middleware services for the enterprise coming up in 2010. Today, our GigiSpace's CTO, Nati Shalom, and Product Manager, Uri Cohen, will discuss GigiSpace's plans to offer on-demand middleware services for the enterprise. I wish you all an enjoyable and interesting webinar. I'll now pass the mic to Nati.
Thank you, Maya. First of all, before I start, I wanted to say a few words about GigiSpaces for those who are not familiar. Our vision in middleware technology is really to enable application to run in a distributed environment if it was one single environment. And that basically has two folds. One is the ability to solve all the distributed problems, high consistency, scalability. And on the other side, it's making it simple so that users wouldn't need to know a lot of those details and would be able to run their application in the same type of environment or the same type of experience that they are used to in today's system. As you can see, we have a list of market customers already been using the product. GigiSpace is out there for more than 10 years. The early adopters come from the financial industry simply because they didn't really have a lot of choice. And we're seeing a broadened adoption of the technology today with online gaming and e-commerce applications and social media. And now I'll talk a little bit about the discussion today and the agenda for today. We're basically going to split the agenda into two sections. One of them is kind of a high-level overview of the topic, which is basically talking about the virtualization of the enterprise and the missing piece in that specific area. I'll then go through some level of high-level overview of the solution to those challenges and how we can bridge that missing piece. And Uri Cohen, our product manager, will go through the technical details and go through some of the new features that is coming with the product and obviously the roadmap and when we're actually going to deliver that. We'll obviously conclude with a summary, which will also discuss the next one. I'll start with the outline of how the current application development cycle looks like today. I try to sketch a little bit of a rough breakdown of a typical deployment. Usually the deployment starts with setting up infrastructure, the network, the computers, the setup and installation, and then we spend time on developing the actual application, the business logic. What you can see here is that typically over time, over a period of 3 years, you'll see that a portion of the actual application development versus the rest of the things, specifically the management and tuning and maintenance, is going to be proportionally very interesting. The management and tuning and the maintenance is going to take more time than the actual development itself. So at the end of the day, what we're finding is that we're spending a lot of time doing things that are not necessarily meaningful for our business, but things that are basically dealing with logistics, integration, and maintenance. Now, the interesting thing is that scaling is actually going to repeat that cycle quite a bit. So if we'll see this cycle, we'll see that the actual scalability will enforce us in many cases to look back into the entire stack and look back into this entire cycle. And that's basically the overhead. And the overhead means that the time it's going to take us to spend proportionally on the application development is going to be even lower with that. Now let's see an example of that I took from one of the projects that we've been involved with one of the, let's say, telco companies. The numbers themselves are not that important because obviously that's going to vary between one project or the other. The interesting thing about those numbers is that you can see the proportion of the actual infrastructure setup and the actual development and licensing setup versus the maintenance cost. What you could see is the maintenance cost is pretty fixed. They're almost independent of the size of the project because of the labor cost and all the things that are associated with that, and it's pretty high. And if you accumulate that at $200K over 3 years, you'll see that the actual cost for the maintenance is going to be substantial compared to the actual development itself. If we add to that the scalability aspect, meaning that we need to repeat that cycle over and over again, then that number even becomes higher. And that's really the main challenge that we were trying to deal with. A lot of the development infrastructure that we've seen today really try to deal with the other parts of the cycle, which is the development cycles and things like that. But most of them really don't look at the actual overhead of the maintenance or try to reduce that maintenance overhead. The things that we're going to discuss today is really looking into a lot of that overhead, specifically around that area, and how we can solve that with virtualization of the entire stack. So let's see the vision around that, which is basically not that new. And I think that most people, when they look at that problem and try to articulate or draw a solution to that, will draw the same picture. What we want is to really decouple the application from the actual resources and automate the entire environment. So as I've taken from the Forrester diagram, which I think illustrates the vision of where we want to go pretty well, what we want is the ability to run the application, run them and allocate the resources to run those applications and pay only for what we use. However, in reality, the picture is going to look a little bit different. If we'll take, let's say, existing virtualization, or even cloud computing like Amazon, and we'll try to apply existing application into that environment, there are a few questions that comes to mind. The first question that I normally ask on that regard is, assuming that we already have that type of environment, what would happen if we add another machine to that type of environment? That would be the first question on that regard. And normally the answer to that that I usually get is that most people would say that nothing will happen. And the reason why is because most of the existing applications were not really designed to run those systems and don't have the means to discover that there is a new machine out there. So even if we have virtualization or cloud computing, and even if virtualization enables us to run or launch a new machine by call of an API, it doesn't mean that the application will know about it and will be able to exploit those extra resources. The other question that I bring in that regard is, what part, assuming that we solve that first problem, what part of the application would be able to consume that extra resources? Is that the messaging? Is that the database? Is that the actual application business logic? Is that the web tier? In most cases, the answer would be we'll have to try and see, which basically translates into a manual work. And that in itself doesn't fit with the vision that I previously showed. So with that in mind, if we look at the last question, which is, let's assume that we even solve that question, and we added a machine, and now we even know that that machine can accommodate, let's say, all the resources that we needed, what would be the impact of the application in terms of throughput, number of concurrent users? And again, the answer in most cases would be that we don't really know. We'll have to try and see, which again translates to a lot of manual work and a lot of sizing. And that's kind of, I think, the introduction to the problem. Now, let's see the solution to that. As I said, we'll break the outline of the solution into two parts, a high-level overview, and the second part, led by Uri, will be drilled down into the actual technical details of that. So here's the picture that we've just seen. And let's take some of the virtualization concept. And the solution is basically, as outlined in the title of this presentation, is to apply the same concept of virtualization that we previously applied into the infrastructure, meaning the hardware, the CPU, the operating system, into the rest of the layers of our application, meaning the messaging, the data, and the business logic. Let's see what that means. What does it mean to virtualize the entire stack? The general idea is basically to take those, I would say, silos that we've built in our tier-based application and break it down into smaller parts. So in this specific example, we could see that previously we had a big messaging server and a big database. And in a virtualized environment, what we really want is to share all the resources, virtualize all the machines. So we don't want to run a machine for the messaging and a machine for the database. We have a pool of machines that will run each one of them. And then we're going to break the data and the messaging into smaller pieces and spread them around into those resources. As you can see here, the application will see all those small, tiny pieces of messaging and data as one big database, as one big messaging. And the way it's going to happen is that they're going to be completely decoupled from those small instances. They're going to have I would say, a proxy that provide a single point of access to all those physical resources, and therefore the application can interact with them as if it was a big piece of machine. Now, in that picture, once we broke down those big pieces into smaller pieces, and we can easily distribute them between the machines, and the application can access them without knowing where physically they are located and placed, let's see what happens when we add another machine. Now, in this specific case, since we already broken down into those small pieces, what we'll basically see is that when you add a machine, unlike the previous picture, we basically add another piece of messaging and another piece of data, which adds themselves to the pool of previous messaging and data, and that means that the application will only see an extra capacity. And in that case, I think that all of the three questions that I asked earlier, meaning what will happen when there is a new machine, how do we, which part of the application will be provisioned to that machine, can be easily solved. We just need to add a machine and distribute another piece of each of the services, and the application will be able to consume them as an extra capacity added to the system. Now let's see how the application can interact with that, and that is something that we refer to as middleware as a service, or elastic middleware. And the basic idea there is that the application itself is going to see all those small tiny resources as one big resources. By that we can maintain the data and messaging pretty much in the same way that Amazon did for SimpleDB and SQS. The application can call an API, and by calling that API, they get the service. They don't need to deal with the provisioning, they don't need to deal with the availability, they don't need to deal with the installation and all of the details, the server-side details of setting up such an environment. That's really the goal behind that idea. So let's see how that works. So the first thing in terms of characteristics is the on-demand part of that. As you can see here, a user asked for 10 gig or 100 gigs memory. Interestingly enough, you could notice that he didn't specify which machines is going to run that request. He didn't need to specify where the actual resources and how many machines will accommodate that request. All he needed is to provide that very high-level abstraction of a request, and the system could actually map that request to the physical resources. So we could actually abstract a lot of the manual work that previously we've done to set up such an environment and automate that. The second part of the characteristic of that type of solution would be the multi-tenancy. Obviously, if you want to run that efficiently, what we don't want is that each user will have its own dedicated machine, because then we'll run out of resources, or we'll have a very expensive or inefficient system fairly quickly. What we want is that when a user, a different user, in this case asking for 200 gigs, not 10 gigs, not 100 gigs, will be able to get the amount of resources, extra resources that is required, but will also be able to share some of the resources with the previous users, as long as they can share the resources. And in that case, we can be fairly efficient. And again, we want to decouple the application completely from, and the details on how we do that, from the users themselves. The last bit, or the third bit on that request, is how do we deal with scaling? Again, we want to be able to deal with scaling completely outside of the scope of the user. The user don't need to know anything about that. Basically, the way we'll do that is by spending more resources or adding more machines into the system in case we don't have enough machines in our pool. And the last bit in that list is the high availability, meaning what happens when there is a failure. In that specific case, what we really want is the ability to, again, automate the failure procedure. Usually what we'll do is if a machine fails, we'll add another machine and we'll alternate to that machine. There is more into that, or we'll go through the technical details of how that failure really works. So I think we've gone through some of the high-level overview of how the interaction between that virtualized stack and the application. Now let's see how Gartners view that, and specifically how they characterize the requirements from what they call virtualized middleware data platform. You can see here the main characteristic, which is multi-tenancy, is the outlined area, resource pooling. I think that speaks for itself, and elasticity and fine-grained usage tracking. All of them really speaks for themselves. I would go through one of the items here, which is XTP grade, which not always people are familiar with. XTP grade meaning that the type of application that we're expecting to run in this type of environment would be transactional system, data aware system. And therefore we need transactional support, but we can't really use the traditional transaction support. We'll have to use the scalable transaction support, something that fits into a scale-out type of environment. And that's where the word XTP is really used in this specific context. Now, Gigaspaces specifically addresses all of those requirements and was designed to address all of those requirements, basically because we were coming from the high-end type of environment of financial industry, and therefore we couldn't really afford losing data or compromise on consistency. And as you can see here, on each of the bullets here, we basically provide a different answer to each of the bullet themselves. So if we could see on multi-tenancy, the middleware itself is multi-tenant aware, which basically means that the actual tenant itself or the actual middleware itself provides the tenancy and provides the support for running in this type of multi-tenant environment. On resource pooling, we're actually providing the ability to pool resources and share resources. Same goes with elasticity, as you've seen in previous slides, and we'll go through the details of that. On fine-grained tracking, and I'll just wait a little bit for the slide to refresh itself. On the fine-grained usage tracking, what you could see is that the metrics and the way we actually meter the environment will have to be fine-grained. We'll have to meter, by meaning of fine-grained, we'll need to monitor not only the application, but also the middleware itself, the replication, the status of the data services, and we'll be able to drill down into all of those details. So I'm not going to go through all of the items here. I think, again, they speak for themselves. Now, let's look at the big picture here. If we look at the next slide, what we'll see is how does that fit into the entire stack. And in that specific case, what we really want to see is, where virtualization fits into that big picture. Is that an overlap or not? And that picture, try to draw where Gigaspaces focus in that area. So our primary focus is really delivering the data and messaging services as well as parallel processing services to enable applications that are running either on .NET or Spring or any other framework to utilize those services and make those services available and run in the type of environment, virtualized environment. So we designed the system and we work, that's really our core effort, is to make those core services fit into the virtualization and bridge the virtualization gap that I outlined earlier. The other thing that we're doing is integration with the rest of the tiers in the application. The main ones would be the web tier, which is basically the front end. In that specific case, what we're adding is session availability, load balancer integration with the web container, all that to really make the end-to-end scalability and the end-to-end elasticity of this environment smoother and not just dealing with the one component of the architecture and leave you the complexity to deal with the rest of the integration. The same goes with the data center support services. Usually what we're expecting to do in a data center or deployment, especially in a production type of environment, is provide a lot of automation on how we maintain the system. If you remember, we talked about maintenance earlier at the beginning of the discussion. Obviously, that's going to be a big part of that, and we introduced already in 7.0 release a new administration API, and we're continuing that path. The other thing that we added is in the latest release is middleware troubleshooting, which basically enables you to get the log file and get the tracing from each of the nodes very easily from a single point of access, security, and real-time monitoring, and we're continuing on that level. I think that would be a good place to start and drill down into the technical review. In that case, I'll let Uri continue with that. Uri, the floor is yours.
Thanks, Nati. In the next 20 minutes or so, I want to walk you through the technical details and kind of how what Nati just laid out translates into our product and into our Gigaspaces offering, and how does that affect our roadmap. So basically, when we look at a certain user, like Nati just mentioned, wanting to get middleware services such as data, messaging, and processing, the user doesn't really care about the low-level technical details. The user cares about the details from the application's perspective. So if we're talking about, for example, a data grid, the user would care about the data grid capacity, minimum and maximum capacity, the isolation level from other deployments. For example, some applications will want to run in a dedicated environment, while others would want to run on in a shared environment because it would save money and it would be more efficient. High availability is another factor that needs to be weighed in. For some applications, high availability is simply critical. They cannot do without it. But for other applications, this is not such a critical requirement. Obviously, they can kind of compromise on that and gain other benefits, such as better performance. So these are the types of concerns that users care about, rather than knowing which host exactly the system runs on, or how it's partitioned, how the data is partitioned across the machines. These are more of the low-level details that they expect the system to handle for them. And that's exactly what we plan to do here. So instead of you calculating and specifying the number of data partitions, for example, the system will do that automatically for you based on the initial capacity that you specified and the existing runtime environment. It will start JVMs for you and choose, for example, the right heap size for the JVMs. It will deploy the data grid and partition the data evenly across the started JVMs. And it will monitor the runtime statistics and the runtime health of the system and take proactive actions in case needed. For example, if the capacity of a certain machine goes above a certain threshold, it will grow. It will add automatically another machine from a pool of machines and provision the system or the missing pieces onto that, like you saw previously in Nati's slides. One thing that's important to mention here is that we are looking at it from a data grid perspective, because this is a kind of a very commonly used or commonly known problem and commonly understandable, but this also applies to other types of services, as we'll see later in this presentation. So the first thing I wanted to show you guys is how this translates into an API. So this is kind of actually a beta API in the next Giga release, and what you can see here is what we call an elastic data grid deployment. And you can see that instead of specifying those low-level details that I mentioned before, like partitions and number of backups and all that stuff, what you actually specify is the isolation level, meaning how you want your deployment to be isolated from other deployments. We'll touch into that in a few more slides. Whether or not it's highly available, and of course the capacity you want this deployment to have. So in this case, we want to start from 1 gigabyte, and we want to specify maximum capacity of up to 10 gigabytes. Another nice thing about this capability is that it will provide what we call hooks to plug into this environment. So for example, when the memory exceeds a certain capacity, you can provide your own what we call a scaling handler to interact, for example, with the cloud environment on which you run on. And in this case, the system will kind of issue this event for you, and you'll be able to provision another resource or another hardware from the environment on which you run, and the system will take advantage of that and expand the capacity onto that environment. Obviously, that can work the other way around. So if you see that you have little capacity or you don't need all the resources you're using, you will be able to get an event for that and shrink down the resources you're using. So this is very kind of fitting to enterprise data centers where resources are shared between applications, or to a public cloud environment such as Amazon EC2. The last bit is the whole security aspect around that, and part of that is the isolation between data grid deployments. So you will be able to specify the isolation level from other users, and of course identify your own data and make sure that this data is not shared with other users on the same hardware. And we'll see how that maps into technical details in a second. So once we saw this API and we talked about what it can do, let's see how it's done actually in practice. So as we said before, the user specifies those high-level details. In this case, we want to deploy a data grid that starts with a 10 gigabyte capacity and can expand twofold up to 20 gigabytes. it can be it needs to be highly available, and in this case we can also specify the size of the JVM that we want the system to use. And we can also specify the multi-tenancy mode or the isolation mode from other deployments. In this case, we use a dedicated mode, and we'll touch that in a few more slides, and we'll understand exactly what that means. So once this deployment request is submitted, basically there's what we call a grid service manager or server that's responsible for managing all those deployments. You can see here that there are kind of two circles here, so this component obviously is highly available, which means that if one of these instances fails, the other immediately takes over and continues to manage those deployments as if nothing happened. Once this deployment is translated, the grid service manager kind of evaluates the runtime environment. So in this case, we can see that we have 4 servers, and those kind of small orange rectangles that you see here represent agents. Agents are a thin layer on top of the operating system with which the grid service manager can communicate. And this layer actually is responsible to get commands from the grid service manager and to start and stop runtime services. So once the grid service manager sees this environment, based on the available memory of each of the servers, it decides how many JVMs need to be started. And in this case, we start 8 JVMs, and that's because what we do actually is that we need 10 gigabytes to start with and up to 20 gigabytes to end with. So that means that we need at least 4 JVMs to host our data grid. And since it's highly available, we'd actually need 8 JVMs because each primary JVM will be backed up by a backup JVM. Now, the grid service manager actually deploys those services. And one thing you can see here is that we have more than one instance of the data grid running on each of the JVMs. And we'll see later why that is important, because this is used for automatically scaling and increasing that capacity. So that's the deployment. Now let's talk about failover. So with failover, what happens is one of the machines can fail. And if you recall previously from the API slide I was showing before, what you can do there is you can hook into the mechanism and actually get this event of a failure or of what we call kind of a missing allocation or under allocation of resources. So there are a few things that happen at this stage. The first thing that happens is that we have automatic failover. So if you look at the data grid instances, you can see that before we had an equal amount of primaries and backups. The green rectangles represent the primaries, and the purple ones represent the backups. And once a certain machine failed, we can see that 2 of the backups became primary to actually accommodate for a quick failover. This is actually a very quick process, takes only a few seconds, and is almost unnoticeable by the end client. Now the other bit is actually restoring the system to its original state, because right now we have a lot of space or a lot of cache instances, data grid instances that are not highly available since one of the machines failed. So at this point, the system is going to issue a command to this custom hook that I mentioned before. And as a user, you can specify, for example, to provision a new image or a new instance of hardware to host the failed services. And the system will start that image and deploy the JVMs onto that. And once the JVMs are deployed, it's going to provision the failed data grid instances. Okay, so this is kind of the situation. Now everything is highly available, but we're still not done, because now, as you can see, the distribution of primaries and backup across the cluster is not even. So the last thing the system is going to do, it's going to switch modes between parts of the data grid instances to make sure that the cluster is up and running and everything is even in terms of distribution of primaries and backups. So that's failover. The last bit is automatic scale-out. So one thing that can happen is that one of the machines can become exhausted in terms of memory utilization. So again, the system issues an event which enables the end client to actually hook into that event and provision new servers in the runtime environment. These could be brand new servers on a cloud environment, dynamically allocated, or this can be standby servers sitting around in your data center actually doing nothing, waiting for them to be used by an application if needed. And the system is going to start the right amount of JVMs onto that, and it's going to migrate part of the data onto the newly instantiated server. So you can see here why we actually needed to create more instances, more data grid instances than actually physical JVMs. This later enables us to mobilize those instances to the newly available resources, and that way increase the capacity. So that was automatic scale out. Scale down would actually be quite similar, only the event would not be high memory utilization, actually would be a lower memory utilization, which you can specify. So once we understood the technical details of how this works in terms of management, let's talk a little bit about multi-tenancy or isolation modes. So the system is going to be able to provide a few levels of isolation, actually depending on the criticality of your application and the isolation level it requires from other applications. So if you're talking about a highly mission critical application that is very sensitive to latency, obviously you would want the isolation to be high. You don't want any other application to interfere with the service level the critical application provides. Whereas in other scenarios where the latency is not as important, for example, back office applications or batch applications that run overnight, this is not that critical. So for these applications, you can actually specify a different level of isolation and actually tell the system, okay, you can use free resources even on the same servers that this application runs for other applications because it's not that sensitive. So we can see here 3 levels of isolation. First of all, what's important to say is that the basic isolation level is a JVM. Each JVM will be dedicated to a single deployment. So under no circumstances, even the kind of least prohibitive isolation level, 2 deployments would share the same JVM. This actually ensures a lot of security in terms of how the application behaves. There's not going to be any thread contention between application or interference in terms of classes and that kind of issues that arise from hosting the same multiple applications on the same JVM. So the basic level of isolation is a JVM. And in a dedicated mode that we can see here on the left, we actually expand that and say that the basic level of isolation will actually be a server. So instead of just limiting that to a JVM, we actually dedicate a server to deployment. So under no circumstances with this isolation level, one server would share the same 2 deployments. Okay, so if we have 2 data grids or 2 applications, they would not be able to share the same server. That way we ensure that the isolation level is the highest possible. The next isolation level in the middle of the slide is what we call shared private. In this isolation, we can actually share servers between multiple applications, but under the condition these applications belong to the same user or to the same tenant, as we refer to that. So for example, if your department hosts multiple applications in the organization, but you don't want to share these resources with other departments, this would be a very good way to go because it would only allow for sharing the servers between deployments of the same user. And the last isolation level of multi-tenancy mode is what we call public. And the public mode basically says that you can deploy multiple deployments of different users on the same server. So these are the kinds of isolation levels that the system will be able to provide out of the box. Now, once we understood how this mechanism works for data grids, I wanted to cover a few other things that you can do with it. So the GigaSpaces data grid was designed and built specifically to be served not only as a data grid, but also as a messaging bus. So with a very simple messaging API, very similar actually to Amazon simple queuing servers, for example, you can actually designate event processors and use the data grid as a bus for events. So whenever you write something to the data grid, a certain piece of code can be notified and react to that event. And this can be done in Java, .NET, C++, or even dynamic languages. Another nice capability you have here is actually execute code on the data grid via MapReduce. So you can actually use the fact that the data grid is deployed across multiple instances or across multiple servers, and use the processing powers of those servers to perform complex computational tasks. And there's a very simple what we call task executor API that again is available with Java and .NET and dynamic languages that you can send code, actually dynamically send code to the data grid to be executed in parallel on all the machines and then aggregate the results back in the end client application. The last bit that I want to talk about is processing and data collocation. Now, once you start a data grid and you're not aware of the of the underlying physical infrastructure, how it runs, this kind of prohibits you from doing more sophisticated or more high-performance things like putting the code where the data runs. So this is also accommodated for by the unique data grid APIs that GigaSpaces provides. And there are two options to actually send the code to be executed with the data. So one thing you can do is ship the code on the fly. This actually is based on the GigaSpaces MapReduce functionality, and you can send it either to all of the nodes in the cluster or to just some of the nodes, or even a single node where you know the data resides. And the code would get executed dynamically on those machines or instances, and the results will be shipped back to the end client or to the application over the network. And the nice thing about this capability is that the code is loaded dynamically. So you can actually define, for example, a Java class at the client side, and the system would know how to ship this Java class and every dependent classes that it depends on to the grid for execution. The other thing you can do is actually use a more kind of static model, and that mode actually means you can deploy the code with the data. So instead of defining the code dynamically at the client and then shipping it to the grid for execution, you actually define it statically at deployment time and send it over with the grid deployment. And in that case, basically the code just sits there and waits for things to happen and gets executed whenever something that the code is interested in happens. So these were two options to actually ship code and save on the latency and save on the network ops in such an environment. The last thing I wanted to talk about is our roadmap for this feature and how it actually kind of integrates with our overall product offering. So all of the functionalities we just discussed would be an integral part of the GigaSpaces XAV product. In 2010, we plan to release two major releases. The first one is 7.1. 7.1, on the Elastic Services perspective, would include a beta release of this functionality, which will include the declarative deployment, as we saw before, this API slide that I showed before, automatic scaling of the resources, scaling out and scaling in, and integration points that it will enable you to utilize virtualized infrastructures in case needed. It will also include the multi-tenancy support. Those 3 tenancy modes that I mentioned before will also be part of the package. The last bit is that we're going to provide a web-based dashboard that will enable you as a user, as a tenant of the system, to actually kind of see what's going on in terms of data and in terms of resource utilization, and access that from any machine that has access to the cluster. In release 8.0, we're going to expand the support of APIs primarily. So instead of writing and reading with what we call proprietary GigaSpaces APIs, you will be able to use JPA, for example, or Memcached, or a REST interface to interact with this environment. So we'd actually use, for example, a JPA entity manager, and this would get translated into calls to the data grid to read and write data from. We'll also support application deployment, as we saw in the last slide and the previous slide, enabling you to ship the code or to put the code with the data and deploy that together into the environment. This is actually the processing unit model known to existing GigaSpaces users. We'll enable a REST interface and a full-blown web-based user interface on top of this functionality. So in 7.1, we'll provide just a dashboard. In 8.0, this will be a full-blown user interface, which will enable a lot more than that. And the last bit is what we call automatic disk overflow. This will actually enable you to deploy your application on much less resources than if you're using just an in-memory deployment. So when the memory gets exhausted, instead of provisioning new instances like we saw before, the system would automatically know how to overflow automatically to the disk and expand the capacity of the system to the disk. So this will actually enable you to pay much less for the same capacity instead of just using memories and instances. So at this point, I would want to hand it over to Nati again for a short summary. Nati, the mic is yours.
Thank you very much, Uri. And I think what we've seen through the presentation is two things. One of them is we've talked about the challenge of maintenance overhead and the complexity of setting up the current middleware. We've talked about virtualization and how virtualization, at least from a vision perspective, is aimed to solve a lot of that by decoupling the resources from the application. And then we've gone through a realization of the gaps that exist today with the current virtualization. And the solution that we articulated was basically to apply the same principle of virtualization to the entire stack, and by that make the deployment and the interaction of the application simple. Later on, we've gone through the details of how we can actually do that through what we call a middleware as a service. And Uri actually went through the technical details showing how that's going to be integrated within our product. The main aim, and that's the kind of main bullets that I wanted to end up with, is really to make an application that runs in this type of virtualized environment very, very simple to use. And that's really one of the main goals for us. From a portability perspective, we want the ability to decouple the application from the data center that they are running, whether it's in a private cloud, whether it's in a non-virtualized environment, or whether it's a private cloud with a virtualized environment like VMware and other things. The other thing is, Rui mentioned, I think, the last bullet is the cost effectiveness. We believe that by sharing resources and applying a lot of the principles that exist out there in the cloud and applying them in our current data center, we could really reduce a lot of the cost of ownership of our deployments. And that's pretty much it. And with that, I'll pass on the mic to Maya.
At this point, I'd like to thank Uri and Nati. We're going to